So hi everyone, I'm Moussa, PhD candidate at Leiden University. I will present our recent work on Tabu-driven quantum neighborhood samplers. So I actually work on studying quantum computing applications, and my PhD funded by Total to study them for those for interesting use cases for industry, such as machine learning and combinatorial optimization, which I will talk about today. So first, I will give a quick overview of quantum computing. And normally I will be very easy. So quantum computing is a new paradigm given by the fact that we're reaching the limits of Moore's law. And so if we try actually to make our current computers small, but very small, then we have to deal with a new type of physics, quantum physics. And then our quantum computers will actually we leverage use quantum physics law, and we'll use actually qubits instead of bits for doing computation. Analogously to what we have classical circuits, we have also quantum circuits. So you have your qubits, you will apply gate operations, quantum gates. In the end, you do what we call a measurement operation, and what you get out of that is a probabilistic bit or bit string as output. So having n qubits means possibly 2 to the power of n bit strings as outputted by that quantum circuit in a random way. Quantum computing is interesting from an application perspective because some quantum algorithms demonstrate possibilities of speedups compared to their classical counterparts, but we could also with them solve some intractable problems, such as the one arising in chemistry, chemical simulations. So quantum computers are here. You may have heard of them in news, but they come limited. It's very difficult to actually design a quantum computer, and it's difficult to scale in number of qubits, which limits the size of problems we can then run at the moment. And this motivates the study of techniques which could still use them, and such techniques as parameterized quantum circuit, which I will talk more in this, which I will talk more about soon. And dividend quantum approaches are very promising approach. Now, parameterized quantum circuit, what you have is you design some quantum circuits, and some gates actually have a real parameter you can set. So by tweaking those parameters to optimize a quantity of interest from the output, generally you tweak them by classical optimizer, then you you just evolve that system towards some an interesting quantity. So, and this is of course very similar to neural network. Parameterized quantum circuits are promising for combinatorial optimization because you can think of the output as having a probability distribution over all possible 2 to the power of n candidates of that circuit. Secondly, those quantum circuits could compute functions or actually probability distributions, which are classically intractable to get. And finally, those can be made to run on a near-term hardware. Now, for combinatorial optimization, there exists an algorithm called QAOA, which stands for Quantum Approximate Optimization Algorithm, which has been designed for tackling such problems. So let's say you have a quadratic unconstrained binary optimization or Ising objective of these types, which encompass a lot of combinatorial problems, then such as mass cut or traveling salesman problem. Then we have to run the following circuit. So actually we start in the state where every possible bit strings has the same probability to be outputted. And as you can see, this is a layered type of quantum circuit, and one layer design is actually dependent on the cost formulation itself. So as a user, you will say, I want to apply P layers, and then you have actually 2 p-real parameters, which we denote by gamma and beta, that you will tweak. They lie in the range 0 and 2 pi. And what you do is you get the output by measurement, so you get many bit strings in the end. And what you can decide is maximize the expected output when you apply the cost function from those bit strings. And I forgot to say that if you have n binary variables, then you need n qubits in that sense. Now, facts and challenges about QAOA. Increasing the hyperparameter P improves the QAOA output. If you tend this parameter to infinity, so if you had that possibility, you would in theory converge to the optimum. It shows some kind of quantum supremacy because from a sampling perspective, it has been demonstrated theoretically that its output is not classically realizable, at least not efficiently. And finally, the problem I mentioned before is that we are limited in hardware, especially in number of qubits. And with QAOA, the size of problem we can solve at the moment and we can run, which make it unlikely to compete with classical algorithms at the moment in terms of size of problems we can compare to. So how to use it in more practical settings? In our work, we actually study one possible solution, which is just combine the technique with a classical heuristic. As such, we study a first incorporation with Tabu Search, where QAOA will actually be involved with Tabu Search by substituting it with the local search strategy used. QAOA is run on subproblems for addressing hardware limitations, and its usage as a local sampler in Tabu Search boosts the any target performance of Tabu Search on QAOA problems we have studied. Now, let's talk about the technique which we can call Tabu QAOA, and let's motivate why we should merge them. So Tabu Search is a simple yet powerful heuristic, or should I say meta-heuristic, because what you have is that you iteratively guide a local search strategy by also leveraging some type of memory structures, which will store, for instance, a certain number of variables, which you will not touch during a certain number of iterations. At each iteration, you will actually explore, the idea is to explore a perturbated neighborhood, perturbated because of those memory structures. And for QAOA problems, what you do generally with Tabu Search is you generate a neighborhood from one bit flip away candidates, which are possible according to those memory structure. So if we talk about variables, and I should consider only non-Tabu variables in this iteration. And you compute this neighborhood by considering one bit flip gains, which is a difference in terms of evaluation of fitness between the current solution, which I denote by X, and a candidates which differ from this current solution by just one bit. And you select greedily the best one at that current iteration from this neighborhood. Now, how do we think of incorporating QAOA? It comes from an intuition that larger neighborhood exploration can be beneficial for your search. And as such, QAOA can be thought as some kind of proxy for exploring this larger neighborhood using just two period parameters and a quantum circuit and the probability distribution which you can get out of it. Then it becomes a flexible tool for exploration-exploitation, which is an important paradigm in every search problem. And finally, we did some error-free simulation on QAOAs up to 500 variables, which is quite large so far with quantum computing. And we took them from the operational research library, so they're open source. They're actually coming from the Bäck GKA instances, and we show that actually in principle we could save many iterations and achieve better solutions by going larger neighborhood. Now, how is QAOA incorporated with Tabu Search? So let's say I select as a user a size of subproblem I want to consider K, which is of course the limit of qubits we have with our technique. So Tabu Search, you start with a current solution. As usual, you compute the one bit flip gains, but of course, looking at the non-Tabu variables. So in our case, our memory structures store for each variable for how many iterations it will be considered Tabu. Finally, with reference to the one bit flip gains, you select the K best variables. Then you create a sub-problem, so a new QAOA, by clamping values from the current solution XTS of the non-selected variable, so the n minus k. Then you run QAOA on the sum problem and you sample out of it. And you select the best candidates from the samples, but also the one bit flip away candidates we should consider as well in this setting. And then you update everything, tabu list, current utilization, current solution, and best solution so far. Also, initially, when I talked about QAOA, as you have seen, the design does not incorporate originally a way to add some the knowledge of a current solution at the moment. So what we actually proposed is to change a little bit the circuit so that we leverage one bit flip gains knowledge that we generate anyway in our Tabu search. And we do so by constructing a new circuit, which is based on adding a penalty to the function. And here you can see this is expressed as such, but you can think of it as a weighted aiming distance from the current solution XTS. And we weight by the one bit flip gain. So the idea is from my current solution, if flipping the JF variables turns out to be beneficial from the one bit flip gain perspective, then I should favor its output from the quantum circuit. Now I mentioned large neighborhood exploration. The first question you ask yourself is if it is beneficial in principle. So we did some simulations where we looked at whether this generating those larger neighborhood by brute force initially. Here are examples of the 500 variable problems, 1F to 5F, onto which I took the best, the optimum. I considered many values of K for the subproblem, and I highlighted in bold the best simultaneous and the least number of iteration achieved. And as you can see, we can find a case such that we can save many iterations compared to the basic TS approach. More interestingly, actually, on our densest instance for F and 5F, we are able to find the optimum in very few iterations, while the basic TS was failing for K equal 20. Now that is said, one will think of, okay, but in overall convergence, does looking at larger neighborhood facilitate it or make it faster? And we address that by looking at two regimes. So where the ratio K divided by the number of variables is greatest when 20%, so we did that on very small instances. And we saw from our runs directly that indeed it is faster, better, it converges very few iterations. And then you have the other one, which is more challenging, and you look at larger instances for that. Which is most of the case, where K divided by N is less than 20%. And here we saw that we needed to tune well the tabu tenure and the K parameter. And what we did then is we aggregated all those runs. So one run of TT is considered one run of a type of Tabu search dependent on K. And as you can see, by increasing K, then I am converging faster. And we did that with those aggregated empirical cumulative distribution functions generated with IOH Profiler, which is a tool for analyzing and for benchmarking optimization runs. And now that is said, so it is faster in principle. Let's look at some QAOA exploration possibilities given. Here I'm showing on subproblems the distribution of QAOA evaluations at very small depth, at depth 1 and at depth 2. And as you can see, you already see an exploration trade-off, where if I limit the depth of my contour circuits, then I am exploring more. And if I increase it, then I exploit more. And not only for us, this is interesting because it could engender new paths because of the exploration-exploitation trade-off, but also because, as I said before, its output is not classically realizable efficiently. And this can be interesting for such strategies as well. Finally, I mentioned this one bit flip penalties adding for the quantum circuit. So here on the right, you see the results of the previous plots. So all the candidates at depth 1 and depth 2 On the right, you see I'm not using the penalty, and on the left, I'm using the penalty. And as you can see, it seems the distribution is smoothened by given the penalty. And this is because the penalty creates an interesting balance between being greedy in considering the sub-problem, but also the one-bit flip gains knowledge we have from the current solution. And for example, if you take this point has higher probability to be outputted with the penalty because this one was actually complying the best with the one-bit flip knowledge we had. Finally, quick showcase of the hybrid approach. This is a 200 variable instance 1E where the basic TS was failing. To find the optimum, with brute forcing the neighborhood show, we could do it normally in 13 iterations. And with QAOA, we were also able to achieve this optimum in the same number of iterations, but we could also have maybe one more, but also one less iteration. So this is quite promising for future. Your search strategies in a way. To sum up, near-term hardware is around the corner, but it's difficult to see their practical value at the moment due to their limitation, to the limitation of the hardware, especially the number of qubits. So for more practical setting, we propose a hybridation of Tabu Search with QAOA, where its usage as a local sampler boosts any targets performance of Tabu Search on QBOS in principle. And this opens the path towards considering sampling aspects of quantum computing for solving combinatorial optimization problem. Our paper can be found at this link, and this is our contact details if you have any more questions. And finally, I should say there is many ways to extend this work in the future, like considering other frameworks, of also looking at running that on real hardware, on different type of hardwares. And that's all for me. Thank you very much for your attention.
Thank you very much for the presentation. So now it's time for questions. Any question from the audience? Okay, then I'll start. Just to make sure I understood correctly, just for the first question. If I understood correctly, so at every Tabu Search iteration, you somehow need to find the best non-taboo moves. And this is more or less what you use, where you use this QAOA approaches to search, to approximate this best non-taboo move towards the let's say 500, if you use a problem size of 500 minus the taboo moves. That's correct? Okay.
Or you using those taboo moves in order to consider some sub-problem, and you generate some kind of neighborhood around that sub-problems also. That's another way to see it.
Okay, I see. And yes, probably my first question would be about, so here at the moment in the Tabu Search that you consider, you use somehow fixed parameterized Tabu tenure, right?
Exactly.
Yes. And I guess you've heard about what they call robust Tabu Search, where they basically, for this kind of problems, where usually you call them UBQPs, but you call them QUBO, yes.
Yeah.
So they're the robust Tabu Search, where actually what they do is very simple. They pick the Tabu tenure randomly within some range. So do you think that your approach is compatible with that?
It is compatible indeed. The problem then is you lose some insight by considering this randomness of the Tabu tenure, right? Also, from what I also heard from Verel Whitney last evening, then we should actually consider less randomness maybe in the future and be more pragmatic. And especially for us as insight, especially when you start designing a framework, you go simpler and then you increase in complexity in your analysis.
Yes. And actually related to this, so also for this problem class, you have a very fast way to evaluate around the neighboring solution. Do you use that in your approach as well?
I do. Computing those deltas actually is we use the strategies that Grover always cite in all this paper.
And I also know that for this problem class, they have also fast way of evaluating neighbors for larger neighborhoods, at least 2-bit flips, maybe more, I think they do. So this, in your case, would be an issue because then this will increase a lot the neighborhood size, right?
Indeed, but at some point, I guess it. Of course, you are limited maybe at 2, maybe 3-bit flips away with the approaches. I'm not sure, and I guess that's why. And that's why maybe considering also larger ones can be interesting as well.
Okay, yeah, it's another way to check for scalability.
Mm.
Okay, thank you. Any other question?
I have a question.
Yes, please go ahead.
Oh, okay. Also, many thanks for the talk. Very interesting. About the quantum circuit, I think you have implemented the quantum module to do the Tabu search. Did you do some optimization in the implementation of the quantum circuit in your Tabu search?
Finding the best parameters for the distribution.
Oh, for example, inserting, for example, swap operations. So this kind of optimization.
Swap operations.
So what kind of quantum circuit do you use?
Oh, just the simple QAOA one, which is of course at the beginning, because this is the original formulation, and I kept with it.
Okay, and so you find some optimization in the parameters in order to implement.
Yes. For that, you just apply a black box optimizer in this case. But there are also interesting properties for those parameters in the sense, let's say you have done some analysis before, then you could actually recycle some parameters you have seen on previous instances and then apply to new ones. Okay. So you could actually even save a lot of calls to this quantum circuit if this is an issue.
Okay,